All right, welcome back. Today we're going to talk about rational expressions and asymptotes. All right, so the first thing we're going to talk about is what is a rational expression. So a rational expression has a form of basically the ratio of two polynomials. So you have p of x over q of x, and p of x and q of x are polynomial functions. All right, so a polynomial is basically something of the form, like a quadratic equation. A quadratic is a polynomial. So ax squared plus bx plus c is a type of polynomial, but it could be any power of x. So in general, well, here, I'll give you an example of one first, and I'll show you the general form of it. So let's say we have 4x cubed minus 2x squared plus x minus 5. So this would be a polynomial where the highest power of x is x cubed, but it could be anything. It could be x to the 100. And then different powers, each term is a different power of x. All right, over something like 10x squared plus 5x plus 1. Okay, so the denominator only goes up to x squared. But again, it could also be anything. So in general, a way of you'll see these written sometimes more generally, is like this. Each of them has a coefficient and a power of x. So let's say you have an x to the n, where n is your highest power of x, and an represents the coefficient in front of it. And then each one has a different coefficient, an minus 1, x to the n minus 1. Then a1, x to the power 1, plus a0 is your constant term. And then the denominator, it's some other set. So I think we call these bm x to the m plus bm minus 1 x to the m minus 1. And then all the other ones that count down until you get to b1 x to the 1 plus b0, the constant term. All right, so that's how you would draw it, write it out more generally. Okay, so these can get kind of complicated. So what we're going to talk about is these a little bit and how to figure out these asymptotes, which we'll talk about in a second. So the simplest one that we know about is this toolbox function 1 over x. All right, so 1 over x, I'm not going to draw it really carefully, but I'll kind of sketch it out here, is the one that looks kind of like this. Okay, so that's our 1 over x function. You can see it's only in the first and the third quadrants. And what happens is it kind of gets closer and closer to the x-axis but never touches it. And also it gets closer and closer to the y-axis but never touches it. And also the same thing over here. All right, so in this case, these lines that they never intersect, in this case it's the x and y axis. I'll try to draw it in red. These are what are called asymptotes. Okay, so asymptotes are basically lines that the function doesn't cross. So it turns out there's there are some exceptions to that, but in general, that's what an asymptote is. Okay. So in this case, we have two of them. We have a horizontal asymptote. So in the future, I'm just going to write horizontal asymptote as HA because it's so hard to write this out. But we have that as y equals 0. So this is our y equals 0 line. So it's kind of weird that it's horizontal. It's basically is the x-axis, but it's y equals 0. And the reason for that is because it can be any value of x, but it has to be y equals 0. So any coordinate on this horizontal line, so 100 comma 0, negative 3 million comma 0, 2 comma 0, all of those coordinates have y equals 0. So it's defined by the fact that they all have y equals 0 and any value of x. And it has a vertical asymptote. And I spelled it wrong already. VA. and that one is x equals 0, which is essentially the y-axis. And again, it's vertical, but it's defined as it's the x value that is shared by all of those points on that vertical line. All right. So those are its two asymptotes. So what we're going to talk about more generally is, given a rational function, how you determine its horizontal and vertical asymptotes. And that's really the main goal that we're going to do for today. And what we're going to do is we're going to learn about that. In the future, we're going to figure out how to apply that to things like the tangent and other trigonometry graphs. And you'll see that the tan function does have these asymptotes. All right, so let's talk about vertical asymptotes of this particular function. So let me just sketch it again. So that's our y equals 1 over x. I think it's sometimes called the reciprocal function. All right, so we have a vertical asymptote. All right, and basically what these are defined by locations in the function where you get an undefined point. So specifically, one thing to remember is that you can't divide by 0. So any number divided by 0 is undefined. And basically these undefined ports tell you where your vertical asymptotes are. So if you can find a point that has a 0 in the denominator, it could be any number over 0, then that's going to be undefined, and that's where you're going to have your vertical asymptote. And because it's undefined at the location, the function can actually have a value along that asymptote. All right. So a notation that you'll see a lot is you'll see something like this. As x approaches 0 plus, f of x approaches. So if you see a notation like this, 0 plus, what you should read this as, here I'll use a different color for this, is you would read this as approaches 0 from the right. Okay, so that's how you should read something like that. So that plus sign means you're approaching 0, but you're approaching it from the right side. And if we look at our function here, right, where the function approaches it on the right side, you can see that it kind of is going upward, like that. And because it's going upward, you say f of x is approaching positive infinity. Okay? An alternate way of writing that that you might see, this is kind of another way to write it, is the limit as x approaches 0 plus, which is from 0 from the right side, of f of x is equal to positive infinity. All right. And then you could also have as x approaches 0 with a minus sign, and you can kind of guess what that means. That means that it's approaching. I spelled this wrong. Approaching 0 from the left, right? Because the left is the negative side, so it's approaching from the negative side. And if we look at that vertical asymptote, and when it gets close, you can see that it gets close during this portion right here. And you could say that f of x is approaching negative infinity. And again, instead of writing it like that, you could also write it as the limit as x approaches 0 from the left side of f of x is equal to negative infinity. Okay. All right, so I think on your homework, there are some things where I give you like a graph, and I give you, I ask you to first figure out where the vertical and horizontal asymptotes are, and then I kind of give you approaching a vertical asymptote from the right and the left, and then you have to tell me if f of x is approaching, minus infinity or positive infinity. All right, so that's vertical asymptotes. Also, we have horizontal asymptotes. Okay. So horizontal asymptotes are where f of x gets closer and closer to y equals 0 in this case as x approaches infinity. So as x goes to infinity, you can see that this line gets closer and closer to that y equals 0 line. All right. And again, there's a similar kind of notation, which is that x approaches positive infinity, f of x approaches 0, it approaches that asymptote, and as x approaches negative infinity, f of x approaches also 0. Okay, so as x goes to infinity, x becomes really large in the positive direction. This gets closer and closer to 0. The y value gets closer to 0. And as x approaches negative infinity, this thing also approaches 0. Okay, so those are the vertical and horizontal asymptotes for this particular graph, and these are just some notations for writing out how that's behaving in kind of an algebraic statement. All right, so here are some special cases that you may see. So it's possible for horizontal asymptotes. So let's say this line right here is a horizontal asymptote. I don't know, let's say it's y equals 3 or something like that. All right, so there's a horizontal asymptote, and then you have a function. So it's possible that the function could look something like this. Now, something you may have noticed here is that there's a crossing where actually this function actually crosses that horizontal asymptote. So one of the things you may be asking is, how can it cross an asymptote? I thought they're not allowed to cross the asymptote. And for horizontal asymptotes, this is not true for vertical, but for horizontal asymptotes, it can cross when you're not at infinity. So technically the behavior is only as x approaches infinity or negative infinity. It either gets closer to that line, but it's possible in the kind of a finite number region for this function to actually cross the asymptotes for kind of small values. All right, so you may see that if you ever come across a function like this. That doesn't mean it doesn't have a horizontal asymptote. Sometimes you do see crossings, but it's really defined as its behavior as you approach infinity. So, so that can happen. So that's just something to be aware of. There's also another kind of asymptote we're not really going to do, but you may see later on. They're called slant asymptotes. Okay, so slant asymptotes might look something like this. You have some graph. And instead of being a horizontal or vertical asymptote, you can have an asymptote that is along a sloped line. Right? So let's say this, you have a slant asymptote and you also have a vertical asymptote. So your function may look something like this. Where again, it doesn't cross those asymptotes at least toward infinity. All right, so we're not going to talk about slant asymptotes, but again, it's something that exists. So if you study more courses, take more math courses, you may see some slant asymptotes. To something to be aware of. I think our book also, if you read the chapter, our OpenStax pre-calculus book, it talks about how to calculate these. All right, so let's do an example. So let's do an example that we know. Y equals 1 over x plus 2 squared plus 3. And if you recognize this is the function 1 over x squared, but it's been shifted. Basically, left 2 and up 3. So if you were to graph this, again, I'm not going to graph this on graph paper, but I'll give you kind of a rough graph. So it's left 2 and up 3. So now this would be kind of the origin, and So those are be the asymptotes for the x squared. If you remember, x squared is kind of like a volcano. So this thing is going to look something like this. All right, so that's our function. Okay, so the first thing that you'd be asked for, I think, on your homework for this kind of thing, is to list the horizontal asymptotes and the vertical asymptotes. All right, so the first thing is our horizontal asymptote is basically this line right here, and this line right here is defined as x equals -2. Oh, I'm sorry, that's a vertical asymptote. I'm sorry. You see, I'm getting confused myself. That's a vertical asymptote, or horizontal asymptote is this one right here, and that goes through y equals 3. So those are our vertical and horizontal asymptotes, right? So those are the lines they don't cross. And then B, you'd have something like this. X approaches -2 from the right. F of x approaches what? And then x approaches -2 from the left. F of x approaches what? All right, so what you look at is you look at this thing, and you're looking at it from the right or left. So now we're looking at it from the right. So when we look at this thing from the right side, we can see that it's kind of going upward. So that's this part right here. So from the right, if we approach -2 from the right, you can see it goes up to positive infinity. All right. If we approach it from the left, we also see that it approaches, it kind of goes to positive infinity. So both of these are positive infinity. All right. Okay, so I'm going to give you one to try for yourself. So I'm going to give you y equals 1 over x minus 1 plus 5. So this is one that shifted, well, 1 to the right and 5 up. And this is a 1 over x function. So I'm going to graph this also kind of roughly. So we go 1 to the right and then 1, 2, 3, 4, 5. So that's our new point there. Here, let's do red as our asymptotes, as a line it doesn't cross. All right, so those are our asymptotes. And if you remember what 1 over x looks like, it looks kind of like this. Right, it's in the first and third. All right, so that's what our graph looks like. And again, what we want, list the horizontal asymptotes and the vertical asymptotes. And then B, to complete this, as x approaches 1 from the right, f of x approaches what? As x approaches 1 from the left, f of x approaches what? All right, so why don't you try that? I'll give you a 3 count, and then I'll go through it myself. Probably be a good idea for you to pause this and try it on your own. Okay, so let's try it. So let's look at our vertical asymptote. So our vertical asymptote is this line right here, and that represented by the line x equals 1. So it's x equals 1 and every value of y. Our horizontal asymptote is this one right here, and this is be a y equals to 5. So y equals 5 and every value of x represents that horizontal line. And then we want to look at as it approaches this vertical asymptote from the left and right. So if it approaches 1 from the right, that plus sign means the right, we're looking at this part right here. And you can see that if we approach it from the right, it's going toward infinity, so this is plus infinity. And then as we approach it from the left, you can see that it's kind of sinking down here, so this is negative infinity. Right? So the 1 over x has different behavior if you're on one side versus the other. Or it could be like this where it's the same on both sides, but they make this notation because you get different answers depending on which direction you're coming from. Okay. All right, so let's talk more about the specific for procedure. Let's say I give you any random, rational expression, and you have to find the vertical asymptotes. So this would be the procedure. So finding the vertical asymptotes. So the ones I gave you before, those were shifts of functions that you already know, but it's possible for me to rewrite them in a way that's not as obvious, to kind of rearrange those equations in a way that wouldn't be clear. So let me take that same equation. So if I took this equation, one of the things I could do to this is I could try to combine these two terms by having a common denominator, and then it wouldn't be in this pattern that you could easily identify. So let's say if I were to do this, one of the ways I would do this is I would multiply the second term by x minus 1 over x minus 1, and the goal of having a common denominator. And what I'd get is I get 1 plus 5x minus 5 over x minus 1. And this would be 5x minus 4 over x minus 1. So let's say you were given this function. So in this form, you're able to easily identify like what the shift looks like, but in this form, you're not. And so I'm going to give you a bunch of functions that look more like this, that you're not going to be able to identify. And that's when you're going to need to use this procedure for figuring out the vertical asymptotes. So the key idea, this is important here. I think this key idea kind of distinguishes whether you kind of conceptually understand this or you're just applying a procedure. But the key idea is this. It's basically you have a vertical asymptote when you get the denominator is 0. And the idea is that you get this 1 over 0 is undefined. All right. So what you're looking for is you're basically looking for the denominator of this rational expression equal to 0, because you want something like this. A number over 0 is undefined, and that's where your function is never going to have a value. All right. Okay, so a more general definition for this is you have some rational expression So there are basically two conditions. The first one is have no common factors. And two, there's some x equals a value. So a is just some number where q of a, which is the denominator evaluated at that point, is equal to 0. Then x equals a is the vertical asymptote. All right. So this is a key thing to think about. Is basically we want to make the denominator 0, but also we don't want there to be a common factors between these two. Another thing, I'm not going to give you a problem that has this, but another thing to look out for is also q should be 0, but it's possible that you can get 0 over 0, and in certain cases that would not be a vertical asymptote. We're not going to go into that too much in this course, but that's something to just keep in the back of your mind, is that it has to be a number over 0, not 0 over 0. All right. So let's look at our function here. So f of x is equal to 5x minus 4 over x minus 1. And our goal here to find the vertical asymptote is we take this denominator and we want to figure out at what point is that denominator equal to 0. And you can see this, you can just add the 1 to the other side, but you have x equals 1 corresponds to the vertical asymptote. All right, so when x equals 1, the denominator is 0, the numerator is not 0, and that corresponds to our vertical asymptote. Okay? So that's the main idea. There's one thing to kind of keep a lookout for, is that part of that definition was that there were no common factors. So what does that mean? All right, so let's say that we have something like this. F of x equals x plus 2 over x squared minus 4. Okay? So I don't know if you recognize this pattern or not, but x squared minus 4 is what's called the difference of two squares. And this pattern basically says if you have a squared minus b squared, that's equal to a plus b times a minus b. All right? So we can rewrite this as x plus 2 divided by x squared, and 4 is 2 squared, which is x plus 2, x minus 2. So you can see that by writing it like this, what happens is that this function does have a common factor. Right? So if you have to cancel out the common factors before you look for those vertical asymptotes. So this is 1 over x minus 2. Right? So then you would take this denominator, then you would set that equal to 0, and you would see that x equals 2 is your vertical asymptote. Okay? Now, if you didn't do that, let's say that you didn't look to cancel out those common factors, what you would have is you would have x plus 2 over x plus 2, x minus 2. And you might think, well, let me make this whole denominator 0. And if you have two things multiplied and they're equal to 0, then you would say x plus 2 is equal to 0, or x minus 2 is equal to 0. And that might lead you to think that you have two vertical asymptotes, x equals 2 and x equaled positive 2. But because you didn't, but that would be false. And the reason it's false is because you didn't cancel out the common factor. All right, so I have hidden one of those in your homework. So see if you can find that one. Don't fall for that trick. You've been given fair warning. All right. The other thing to look out for is the case where there are no vertical asymptotes. All right, so it's possible that there are no vertical asymptotes. So let's say that we have something like this. F of x equals 1 over x squared plus 5. All right, so again, you might just say, let's take the denominator. We can't cancel out any common factors. Let's take the denominator, set equal to 0. X squared plus 5 is equal to 0. We subtract the 5. We get negative 5. Square root both sides. We get x is equal to plus or minus square root of negative 5. Do you remember what happens when you have a negative under a square root here, or square root of a negative number? That makes it imaginary. So you get x is equal to plus or minus I square root of 5. So this is imaginary. And we cannot, we can't plot an imaginary point on a real axis, okay? So what this means, if you get an imaginary number here, that means that there are no vertical asymptotes, okay? And actually, this might have been something that you would have guessed just by looking at this. So if we look at this, x squared plus 5 is equal to 0. One of the things you know about x squared is that it's always positive. Right? And because it's always positive, you have a positive number plus a positive number can't be equal to 0. Right? So you can't cancel the 5. So this equation can never be equal to 0. There's no number you could come up with x, positive or negative, that would give you a number that would cancel this out. So that would be a case where there are no vertical asymptotes, because there's no power of x that you plug in that would give you a value of 0. All right? So if you run into something like that, you see a square root of a negative number, that's a clear sign that there are no vertical asymptotes. All right, I ran out of paper. Here, let me get more. Okay. All right, so let me give you some to try. You try. And your goal is to find the vertical asymptotes. All right, so here's the first one is 5x over x minus 4, x plus 7 over x squared minus 49, and 2x squared over x minus 2 and x plus 6. All right, so why don't you try to find the vertical asymptotes. Again, you can pause the video and try it yourself. I'm going to count to 3 in my head, and then I will go through it. Okay, so let's go through it. So the goal for this is basically make the denominators equal to 0. So this first one, x equals 4, is the vertical asymptote. Again, something I like to check also is make sure if I plug in x equals 4 to the numerator, make sure the numerator isn't 0 either. So that's good. All right, this one, when I look at this, you might think, oh, I'll just make x squared minus 49 equal to 0, but you have to be careful here because remember that you have to cancel common factors. So this is another example of a difference of two squares. So since we have a difference of two squares, I will factor it out. And what I find is that I can cancel out this x plus 7. And because I can cancel out that x plus 7, this simplifies to x minus 7. And then what I do is I take that and I make that. And I get x equals 7 is my vertical asymptote. All right, x is negative 7 is not a vertical asymptote. So remember, keep track of that. Look for that trick on the homework. All right, these nothing cancels, so I'm going to take this. I'm going to take these and make the denominator equal to 0. Okay, so if I have two numbers here, this parentheses and this parentheses, two things multiplied equal to 0. Either I have to have one of them equal to 0, or I have to have the other one equal to 0. And that gives you two different solutions. X equals positive 2 and x equals negative 6. And both of those are your vertical asymptotes. So this one has two vertical asymptotes, one corresponding to that term being factor being 0, and the other one, or that factor being 0. So that's how you find vertical asymptotes. So you'll have some homework problems that give you an equation and then ask you to find the vertical and then the horizontal asymptotes. So that's what we're going to go through now, is finding horizontal asymptotes. Let's use black. So finding horizontal asymptotes. All right. So again, this same function we had before. 5x minus 4 over x minus 1. So we had a function that looked kind of like that. And this one had a horizontal asymptote. I think I left out a y there. At y equal to 5. All right. So how would you figure out the horizontal asymptote? So again, there's a key idea here. And the key idea is basically find the value as x approaches infinity, or x, there's also another saying, x is large. All right, so when x is really large, what does the value of the function tend toward? All right, so I'm going to do a little sidebar. I'm going to call this sidebar approximation at large values of x. Okay, so how do you approximate a function at large values of x? So we're going to do a little experiment. I'm going to give you a function. Let's say f of x is equal to 3x squared plus 2x plus 1. And we're going to plug in a value. So this for this function, we're going to plug in a value of 100. So this number isn't even like that big, but it's big enough for our purposes, and we'll see here. So I'm going to plug in 3 times 100 squared plus 2 times 100 plus 1. Okay, so if you actually calculate this, 100 squared is 10,000. So what this becomes is 3 times 10,000 is 30,000. This is 200, and this is 1. So when we calculate this, this is 30,201. So one of the things you look at here is like which of these was most important, right? So when you look at this, basically, it's that 30,000 is way more important than these other things, right? So that basically comes from this 3x squared. Okay, so if we wanted to approximate this, it would not be a bad approximation to say that f of x is approximately, so if you see these squiggle lines, that means it's approximately equal to 3x squared for large x values. And so the number we picked was 100, but it turns out the bigger this number is, the less and less important these other terms are compared to this first one. The 3x squared is going to be, whatever the highest power of x actually, is going to be the most important one. All right. So our general rule that we're going to do here is, x approaches infinity, which basically means x is really big. We're going to say f of x is approximately equal to the highest all right, I should have said this a little bit differently. It's equal to the highest power of x term. So in this case, the highest power of x was x squared, so we only kept this term with its coefficient, and we dropped off all these other ones. And that's what we're going to do in general for figure out these horizontal asymptotes. Okay? All right, so let's do an example of that. So we have y equals 5x minus 4, and x minus 1. So what we're going to do is we're going to say this is approximately equal. And again, what the approximation says is we only keep our highest power of x, and then we drop everything else. That's what this is approximately equal to. So we get 5x over x. These x's cancel to give me 5. And what that means is that y equals 5 is my horizontal asymptote. Okay? That's literally all we're going to do, is we're just going to keep the highest power of x in our numerator and keep the highest power of x in our denominator, and then get rid of all the other terms. All right, so that's basically the strategy that we're going to use. Okay. So there are 3 cases for the horizontal asymptote that you have to be aware of. So let's say we have some function f of x, which you can write as like an x to the n, and then it has all these other terms, over bm x to the m, and it has a bunch of other terms. We're going to approximately say this is equal to just the highest order term. And we're going to get rid of all the other terms. That's basically the whole idea here. So our 3 cases. The first one is where n is less than m. So here I give you an example here. I'll do the examples in green. Let's say we have 3x squared over 5x to the 4th. So in this case, n would be equal to 2 because it's that's the highest power. X squared is 2. And then m is equal to 4. And clearly, n is less than m. And in that case, if you were to do this, what happens is some stuff cancels. So you get 3 over 5x squared. And then as x gets really big, this is roughly 3 over infinity, which approaches 0. So that says the horizontal asymptote is y equals 0. So anytime you have a situation where the power of x in the denominator is bigger than the power of x in the numerator, you're going to get y equals 0 as your horizontal asymptote. The next one is when n is equal to m. So an example of that, here I'll just use a different color for each of these, is let's say 5x over 2x. In that case, n equal to 1 and m is equal to 1, x to the 1 and x to the 1. So if you do this, 5x over 2x is equal to 5 over 2. And in that case, y equals 5 over 2 is our horizontal asymptote. So what happens if they're the same power of x? You can just cancel them out and just keep the coefficients in front of them, and that's your horizontal asymptote. All right. So this is also the same as saying the horizontal asymptote is whatever the coefficients are, an over bm. Okay. C, case C, is when n is greater than m. So an example of this, here we'll use red, is 3x to the 4th over 5x squared. And here n is equal to 4, that's the power 4, and m is equal to 2, power 2. And if you do this, 3x to the 4 over 5x squared, this becomes 3x squared over 5. And what happens is that this approaches infinity divided by 5, which is infinity. And so if you have a situation where as x gets really large, this ratio also gets really large, that means that there's no horizontal asymptotes. All right. So it turns out, and your book talks about this, if you read the section on asymptotes, is that in this situation, it's possible that you could have a slant asymptote, and they show you how to calculate those, but we're not going to get into that. Okay, so I'm going to do some, and then I'll give you some to try out, and we'll wrap up this lecture after that. So let's do some where we find the horizontal asymptotes. All right, so f of x is equal to 4x over 2x squared plus 1. Okay, so what we're going to do is we're going to approximate this. So again, the way we approximate that is we keep the highest power of x in the numerator and highest power of x in the denominator and get rid of everything else. So we get 4x over 2x squared. And then we can cancel out a 2 and cancel out an x. So we get 2 over x. And as x gets really large, this is going to approach 2 over infinity, which approaches 0. So our horizontal asymptote is y equals 0. Okay. B, g of x is equal to 4x squared over 2x squared plus, let's say, well, I guess we'll just leave it as 1 also. And again, our strategy is to keep the highest power of x and get rid of every other term. So we get 4x squared over 2x squared. And what happens is the x squareds cancel, and we just get 2. And that tells us that y equals 2 is our horizontal asymptote. Case C, h of x is equal to 4x cubed over 2x squared plus 1. And it's the same story here. Keep the highest power of x term, the term with the highest power of x, and get rid of everything else. 4x cubed, 2x squared. So you get 2x. And then this thing is approaching infinity, And if it does that, that's a sign that you have no horizontal asymptote. Okay. All right, so I'm going to give you some to try. So you try these. 15x over 3x squared plus 1. B is 12x squared over 3x squared plus 1. And C is 9x cubed over 3x squared plus 1. All right, so why don't you try those? I'm going to count to 3. You can pause the video and do it yourself. Okay, so let's do this. So again, let's approximate these. Again, we're just going to keep the highest power of x. For x is really large, we only need that's a pretty good approximation. So this becomes 5 divided by x. And this is approaching 5 over infinity as x gets really big, which approaches 0. So y equals 0 is our horizontal asymptote. This next one, again, keep the highest power of x. 12x squared over 3x squared is 4. So y equals 4 is our horizontal asymptote. And then this one approximates to 9x cubed over 3x squared, which is equal to 3x, which approaches infinity, which means that we have no horizontal asymptotes. I probably should have mixed them up so they're not exactly the same order, but that's basically how you do them. All right, so now you know how to figure out vertical asymptotes and horizontal asymptotes. I want to give you one where you have to find both because you have most of your homework is, I'll give you a function and you have to find both of them. So I want to do at least one where I do both. So f of x is equal to 2x squared over x squared minus 1. Okay? Okay, so let's do our vertical asymptote first. So our vertical asymptote is when this denominator is equal to 0. But the first thing I look at here is I realize it's a difference of 2 squares. So I know that x squared minus 1 is equal to x plus 1 and x minus 1. And the next thing I would look for is whether that actually cancels out any factors here. But there's no factors. This does not have an x plus 1 or x minus 1 factor. So it's not going to cancel. So you just want to check to make sure that's true. So you want to make that denominator equal to 0. So I'll leave in this factored form. So what that means is either this term is 0 or this term is 0. One of these has to be 0 because when you multiply two numbers, the only way you can get 0 is if one of those two is 0. So anything times 0 is 0. So x plus 1 equals 0, which means x equals minus 1 is an asymptote, vertical asymptote. And x minus 1 equals 0, which means x equals positive 1 is also a vertical asymptote. So if we were to graph this over here, we have vertical asymptotes at x equals 1 and a vertical asymptote at x equals minus 1. All right, now let's look at our horizontal asymptote. So our horizontal asymptote, what we do is we take the function and we approximate it by just taking the highest power of x. So I get 2x squared, and then I have x squared minus 1, so I'm going to ignore the 1 and just keep this x squared. And what happens when I do that approximation is the x squared cancel, and I just get 2. So I get y is equal to 2 is our horizontal asymptote. All right, and so if we have our horizontal asymptote is right there. So I'm not going to get into actually drawing these functions. There are methods to do it. The book chapter talks about them. If you really wanted to graph it, I mean, one way you could do it is you could just plot points, just sort of figure out what value it is at various points and try to plot it and figure out what it looks like. you can put it on Wolfram Alpha or some other graphing software to do it. But for this homework, basically, I'm going to give you a function like this, and then you have to go through a procedure where you find the vertical asymptotes and a procedure to figure out the horizontal asymptotes. I think that's like, I don't know, 8 of the questions on this next homework. This homework is homework, I didn't write the number down for it, but this one is due in a week. All right, so I hope you are safe and you're doing well. If you have any questions, please feel free to reach out to me by email. If you'd like more, we can set up phone calls, or I can do some sort of open digital office hours I've heard some people are doing. If that's interesting to you, just let me know. All right, so I'll talk to you next time. Bye.